Hi, everyone. Thanks for joining this session. My name is Ivan. In this talk, I'm going to talk about anomaly detection time series. I'm going to share the journey of our small team of implementing a solution that we now use. And another disclaimer, this is mostly about business metrics. So it's not about system metrics. It's primarily like detecting anomalies in the behavior of the users. First, a bit of a small introduction. I'm Ivan. I'm originally from Ukraine, but I live in the Netherlands for 13 years. I'm working as site reliability engineer at Booking. Before that, I worked at TomTom and spent the majority of my career in eBay Classifieds group before it was sold. And in my free time, I really enjoy working on my open source projects. So you can check out my GitHub page, LinkedIn profile. So let's get started. So whenever the topic of anomaly detection comes up in some teams, and I have seen this over and over again in different companies and various teams, they go for the easiest solution possible, given that they don't have any existing tooling available in the company. And what they do is they typically just create a Grafana dashboard, put some current week metric, and then they also put the same metric but 1 week ago. So they compare how it did today versus 7 days ago. Well, this solution might work for a bit, but there are obvious flaws with this approach because whenever you run into an outage, that's going to become your baseline for the future. So if you're having the outage on the same time of the day and you're matching the same drop as on this example, then obviously that's not going to work out. You will miss it. Another problem with this approach is that you're limiting yourself to only 1 week of data. And even here, it might look like you're overperforming. It's only when you add additional weeks and you expand your view into the second, third, and fourth week, you will notice that actually we are underperforming in the last week, in the current week. This is what we wanted to achieve in the beginning of what we set ourselves as a goal. And this is, by the way, a real screenshot of a real Grafana dashboard that we're using for detecting anomalies. And the idea here is that instead of coming up with some prediction metric and making a simple difference between the current metric and the prediction metric, we come up with the prediction range. And with this, we have some kind of like sort of like a control for giving us a confidence range for the value that we expect. Because we cannot know for sure what we should expect at the exact time, because some metrics fluctuate a lot, and with this, we would have some kind of influence on the confidence range. Basically, if we are within the range, then we're fine. As soon as we go outside, we're 100% certain that that is an anomaly, and we want to detect that. But the main focus was actually detecting these so-called slow burns, and those are the most annoying incidents that we had, because typically when that happens, we don't have any other alerts and everything works fine. It's just that something is, we have like some small underperforming, and at some point it keeps on accumulating. And what is even worse, that it might be actually related to a configuration change or A/B testing, feature switch, anything, some external events, but it could also be delayed. So you don't always see an incident right away. It doesn't manifest itself right away. It might be delayed by an hour or a day or even a week. So the sooner you detect these things, the better, because it might take some time for you to get back to normal shape in your business metrics. So we thought like, okay, what can we do? Can statistics help us? And I just want to quickly interact with the audience, get a feeling. How many of you know what the standard deviation is and how to calculate it? Cool, almost everyone. And who knows what Z-score is? Okay, fewer people. So if I put it in my own words, how I can explain in my own words what standard deviation is basically a simple instrument, and it's a single value that helps me measure the dispersion in my data set. But if I apply this logic to the time series, basically it will help me to measure the like a fluctuation in my time series. So if my time series shows a straight line, it doesn't matter what the value is, the standard deviation will be 0. And if I have a bigger fluctuations in the time series, then the standard deviation will be bigger. And I thought that this could be a really good use case for building a prediction range. Z-score is a way of measuring how far you're, of any point in a data set, how far a particular value is far away from the average. And the formula is very simple. So you just take a particular value. You can do it in a for loop in your time series if you already know the standard deviation and the average. And if you follow this formula, it simply measures how many standard deviations is it far away from the average. And if it's minus, then it's below. If it's plus, then it's above. Simple as that. So we thought, okay, can we do something like this? And it's, by the way, not our original idea. This is something that we have researched, and some companies are implementing this approach for anomaly detection. I saw some examples doing this in Prometheus. Oh wait, sorry, I forgot this slide. So another thing with the z-score, that you can also convert them to percentages. And a normal distribution, it works like this. So if you have a z-score of 0, that means that you're exactly on the average. So that also represents 50% of the data if you sum off the data points below the average. If you expand the standard by 1 standard deviation, it will be 84. You keep on expanding, you get a bigger z-score, and it keeps converting closer to 100%. So with a z-score of 3, you end up with a 99.87% of observations in your data sample. And that is, by the way, a really nice threshold, because with this one, you can sort of like use z-score to detect the outliers. So getting back to the anomaly detection, the idea is as simple as this. Imagine that we have some weak graph, some metric, some business metric, and there's nothing special about this metric at this moment, right? You don't notice any obvious outliers, any obvious anomalies, etc. Just a small decline towards the end. It's only when we add more weeks of data, like for the same time of the day, but in different weeks, it becomes obvious that there's something going on towards the end. So how can we easily detect that using these basic statistic tooling available? So we first come up with the average based on the previous week within some time window. And then we would calculate standard deviation. And once we have average and standard deviation, we can use that simple formula to calculate z-score for every single point. So in a for loop, we just go through all the points in the metric, and we come up with the z-score. And you already can spot the pattern. The majority of the data points, where they sort of like align with the previous week observations, they are within 1 standard deviation. But the ones that are really low, those show up as less than -3. So -3 is actually a good threshold, and some other companies were also using that threshold for detecting the anomalies. So if we use that threshold, we declare those 4 data points as anomalies. So it should be easy to alert on this metric. That's the idea. So the next question is, can we use graphite? And again, quick question, how many of you are familiar with graphite? Cool. So Booking has a lot of metrics in graphite. It has an enormous cluster, graphite cluster, and not all the metrics are in Prometheus. So, and because a lot of business critical metrics are in graphite, we were only limited to that. So we thought, is there a way to not build anything complex and just do it with what graphite can offer? And interestingly enough, it actually was possible. So we managed to build a simple dashboard only relying on graphite queries, using Grafana dashboards with some heavy overrides. In this case, they're not that heavy, but I'll show examples later of more advanced usage. And we were able to detect some anomalies using the z-score calculations. So we detect the anomaly drop by showing it in the red bars and anomaly spike in the blue bars. So how we did it? Unfortunately, graphite doesn't offer a z-score function. But what we did is, if we would have some kind of business metric in graphite, we would then create 4 or 5 additional metrics with a time shift function. So we basically take a time shift of 1 week. So we're going back 1 week ago, 2 weeks ago, 3 weeks ago, etc. So that's the same idea as I showed you earlier in the simulation. Once we have the time shift metrics, time shifted metrics, we send them into the standard deviation series function that calculates standard deviation of the multiple metrics. We do the same for the average, and then once we have average and standard deviation, we calculate the difference between the current metric and the average, and then we divide that by standard deviation, giving us the z-score. That's the basic idea. I had to make this demo because I originally created a screenshot of the dashboard, and it was enormous. It was difficult to explain it on the screenshot. Unfortunately, this solution doesn't work well, and it quickly falls apart whenever we encounter previous anomalies. So whenever we have an outage, that's going to leak into the prediction range calculation next week. So if there is even one small anomaly in the past, it will severely affect the prediction range. Not a good thing to have. So we thought, okay, is there a better way to measure this? And that's when we, first I'm going to show you the effect of the small anomalies on the calculations. So if we take various weeks of data, calculate their average and standard deviation, we come up with in this example, 17.6, right? Now imagine that we just drag a few points on only 1 week. So simulating a small, kind of like a small outage, small drop, right? the new average based on that data will not change that much, but the standard deviation grows by 80%. So apparently, that actually explains it. And if we had a bigger outage, it would grow even more, right? We thought, is there a different mechanism? And apparently there are different ways of measuring deviations in statistics, and one of them we found it's median absolute deviations, which are now my personal favorites. They work a bit differently. Instead of the square root, you have this sum of all the absolute differences for the point versus the median, divided by number of samples. And what is funny, what is interesting, it's actually performs better in that particular simulations. So if I run through exactly the same data points, same simulations with the incident, I would only have 31% increase. That was a good learning for us, that different deviations perform differently with the same outliers. Unfortunately, 31% is still too much, and it's not very precise. And Z-score-based approach for detecting anomalies has also its own drawbacks. That's at least from our experience. The first one that we notice is that it's very sensitive in the smaller deviations. And this is not some theoretical example. Imagine that you have some business metric like orders on your website, and you're tracking the orders in one country. During the night, the orders will decrease because users prefer to sleep during the night, so they are less active on the website. And you will have, with a lower number of orders, you will also have smaller fluctuations in the time series, causing smaller deviation, therefore triggering the Z-score-based alert more often during the night. Another thing that we found out is that it's not very practical for alerting itself. Even though you can put a better alert than this one, you can give a better summary, if it relies on a graphite metric, for instance, the calculated Z-score metric, you would still have to click the link to go to the Grafana dashboard. You will see a change in the Z-score, but it will not give you too much of information on how to actually measure the impact. And a much better metric would be how many orders have we lost within the last 10 minutes. So we wanted to make it more practical. And that's when we realized we're limited by what graphite can offer. Also, one thing I forgot to say, that graphite, contrary to Prometheus, doesn't let you query multiple data points in a metric and then send that into a function. So you're always limited on the same time interval. So we're limited on that one. And that's when we realized, okay, what if we try to build a simple service that would perform these complex calculations that we cannot do in graphite? And the idea was that it would take graphite as a data source, and for Anomaly, it's like just an abstraction. We could also switch it to Prometheus. It doesn't matter, it's time series. So it reads some business metrics from graphite, computes the prediction range that it thinks it's going to be for this time of the day, and sends it back to graphite later to be used in Grafana. And with this, we're going to detect those slow-burning events and also the large sudden outages, so big spikes, big drops in the metrics. And the priority number one was to figure out a way to exclude the past outages and not leak them into the calculations for the prediction range. And that's why we had to resort to building our own simple service. What we wanted also to achieve, we didn't want to spend a lot of time building some service. We wanted to only just implement the calculations, but the actual anomaly detection and how we want to detect anomaly, we wanted it to be left to the Grafana dashboard so that we could experiment. And once we would be pleased with the result, we would then later implement those additional calculations into the service and simplify Grafana dashboard. And another thing that we wanted to achieve is also be able to configure holidays, various known events. So for instance, if we know that there's going to be a holiday or some kind of big event and we expect underperforming in the metric, we want to have some kind of influence on the thresholds for our alerting. So those were like the goals that we set up for ourselves. And we started building a service. That's the high-level overview. It's very simple. So Anomaly, it just works as a background job, calculates. It takes metrics from the graphite, then for every minute it calculates the prediction range and sends the data back to graphite. And with the solution, we have a lot of freedom how we want to do that. So unfortunately, with that freedom, we got a lot of complexity in the dashboard making process. So we quickly realized we need to resort to dashboards as code, and I'm going to cover that in the last slides. So we manage dashboards as code, and then we update the Grafana dashboard through Terraform. And the Grafana is the one that actually detects the anomalies by relying on Anomaly metrics. So the service called Anomaly, I forgot to mention that. So how Anomaly works? We decided to go for a bit different approach, not relying on a standard deviation. And the idea is like this. Imagine that we have multiple, so we give it a particular metric that we want to detect anomaly for. The service would then query previous week's data for that metric. And then, it will sort of like virtually align them on the same time of the day. And if the service, if we were currently at this time, so this is the time for which we want to detect, to calculate the prediction range. The anomaly takes the first parameter, which is called window, and in this example, it's 40 minutes, which means we're going to take 20 minutes left and 20 minutes right, and only within that time frame, within that time window, we would take the data points from the multiple previous weeks. And the next step would be to sort them by value, and then the next parameter kicks in, which is called percentile, and with this approach, we wanted to take the percentile from the low end and from the high end. So if it's percentile number 5, then we will take a 5th and 95th respectively. The idea with this approach would be that we would have some kind of control of filtering out the outliers. We wanted to remove those anomalies from the past. And then once we have we calculated those become the upper and lower boundaries for the prediction range. And if we repeat this process like for every single minute, we end up with this graph with where we have two metrics, the upper and lower bound. So once we have that, it's very easy to set up alerting in Grafana and then do some more logic on the anomaly detection. But to get these, we had to come up with these calculations on the service. So next thing that we also decided to work, and this was an interesting learning, is we came up with this sort of like a very simple simulation page that would let you put any metric from Graphite and first test it how it would look like before putting it in production. Because not every metric is actually suitable for anomaly detection using this approach, because this approach relies on the pattern-based metrics. So primarily metrics driven by users, because users show a lot of signs of pattern in their behavior. So for system metrics, it might not work, and you could test how it would look like. Well, I mean, for some of the system metrics, it might not work. Another thing, you could play with various parameters, how it would look with more weeks of data, how it would look with a higher percentile. You could manually expand the range. And another one on the right-hand side, there's this additional simulation for the distortions, which was actually key for us to polishing our algorithm for outlier exclusions. Because we could not always you have a luxury of having an incident in your time series to play around with. So we decided to just simulate distortions and see how we could effectively filter them out. That was very helpful. So it didn't go well. It did go well for a bit, but then we ran into a lot of various interesting problems, and I'm going to cover all of them in next slides. The priority number one was excluding past anomalies. So this is just an example of how it would look like if I would take a same business metric and then put multiple previous weeks, and some of them might have anomalies, some distortions, as you can see, right? If we just take blindly the 5th percentile using the Anomaly approach for taking the percentile for the lower and upper bounds, that's what the prediction range would look like. Not very useful at all. But if we increase the percentile, it actually does eliminate some of the outliers, so it makes it much better, but there's still one large bump in the middle, which is not acceptable for us. So we tried to figure out, okay, how can we do it in an easy way? We didn't want to introduce state, like for instance, you could say like, oh, you could, if you detect an anomaly today, you can mark it and then keep it somewhere in the database, and next time you just throw it away. We didn't feel like that would be a good solution, and we wanted just to resort to something more simple. The first thing that we would try was a very naive approach. It's just trying to remove only 1 week at a time. So imagine you have 4 or 5 weeks, and you're only allowing yourself to exclude 1 week from the calculations. And then you're trying to do this for every single week until you find what is giving you the least standard deviations. So if you remove the biggest outlier, it will cause you the least standard deviations. And that works a little bit, but it doesn't work when you have 2 anomalies close to each other from various weeks, or when they're overlapping. And if you increase the percentile, you might get rid of that bump, but you have a lot more artifacts in in the positions where you didn't have any anomalies at all. And that's when we come up with a different solution. I'm not sure if that's already used somewhere, but we just call it a cherry-picking outlier exclusion. And the way it works is like this. We analyze, let's say we analyze data point at the same time of the day for multiple weeks. We put it like this. And right now for you, it's obvious that there is one outlier. Probably it needs to be excluded. Probably it represents some kind of anomaly in one of the weeks. Week number 1, right? It shows like it's 200. And then the other ones, they are closer to 600. So what we do is we calculate absolute z-score. So why absolute? Because we don't care if it's below or above the average. We just want to see that it's far away from the average. So we want to measure how far away is it from the average. Actually, in this case, we switch to median absolute deviations, but it doesn't really matter that much. And the next thing that I'm going to show you might look a bit weird to you, but I'm going to explain you why it works in the next simulation. So what we do here, we take the median out of all the calculated z-score, and then we do the so-called like normalization, where we subtract the median from the z-score, thus giving us a better view of which one should be treated as outlier, because we have some configurable threshold that any leftover that is higher than 1 is marked as an outlier and excluded from the calculations. Now, why do we do this weird thing with the median of the z-score? In the next example, we might encounter like a normal behavior. There were no anomalies, no incidents, and the data sample looked like this. If we calculate z-score based on only that data alone, it will still show up the first and the fourth week as the outliers compared to the second and the third week. Simply because the week number 1 is above is the highest value, and the week number 4 is the lowest. But this is where this median trick comes in, and if we do the median and we repeat this normalization process, they will not pass the threshold, so all of the data will stay there. And that's pretty much it. So if now repeat it through all the data points, we will get this prediction range. So I hope you can see it. Yeah, you can see that there's exactly the same anomalies, and it did come up with a nice prediction range. And to our surprise, it even worked well with with overlapping anomalies. So not always. So in some heavy simulations that we did with adding like really a lot of distortions, it might not work well. But looking at least for all the metrics that we built, we actually never had any problems. It worked effectively, eliminating the past anomalies and building a nice prediction range. So now challenge number 2. I really hate this. This is daylight savings time change, and just also please raise your hand who hates daylight savings time change. Yes, I'm having issues sleeping at night because of this. I need to get used to it, but so are the users. And the other problem that we notice is we relied on the time shift function in Graphite. And it simply works as you give a time shift, the first argument of the metric, the second argument for how far away you want to go. And we'd say, go 1 week ago, 2 weeks ago. But Graphite doesn't really care about daylight savings time change, and it simply takes 168 hours in a week and goes back. But if in the middle there was a daylight savings time change, you're now misaligned. You're not showing for the same time of the day. And this is what is important, because we want, like users, they prefer to stick to the same time of the day, typically. And we had to fix it in a different way. We had to get rid of all the time shift functions in our calculations, in our Graphite queries. And then we came up with a simple code that would calculate us the same time of the week, same time of the day a number of weeks ago. And it works as simple as just give it a current time, give it a number of weeks ago. It would get time zone offsets for 2 times, get the difference, and then use that difference to compensate for the daylight savings time change. So it always gives the same time of the day, even though you had a daylight savings time change. Unfortunately, that didn't solve all the problems. So we did manage to align the metrics a bit, but the pattern actually changed. And the problem here is something that we actually didn't solve yet. It's Booking is a worldwide company serving multiple countries. Not every country implements daylight savings time change. And also, even within the same country, there are some users that don't adapt it right away. And that was causing distortion on the x-axis for the metrics. And so far we haven't yet fixed this because it only happens 2 times a day and it's for a short period of time. So, and it's also not that easy to simulate it. It's not just a simple 168 hours, like 1 hour mismatch. It's actually more than that. It's the behavior of the users is changing. Problem number 3 is very interesting one, and I really like it a lot. It's when you're suddenly overperforming. So it happens sometimes. For instance, you might underperform one day because of some events, and then the day after, all of a sudden users getting back, and then all of a sudden you do not expect that behavior, and you're overperforming in your metrics. So you have prediction range based on the past, and you didn't expect that you're going to do so much better this day. But let's say you're overperforming by 20–30%. What if there is an incident that causes outages for like 20% of the users, and you're missing then that instant? If you would go as simple as that, it will go undetected. This is where we came up with the idea of the origin adjustment. So we would adjust the metric to the prediction range. And the way it works is we come up with this, well, it's not it's a simple calculation. We come up with the second metric, adjustment factor. So we take the original metric, we multiply it by the adjustment factor, which is also a metric, and now we get the adjusted origin. And the way the adjustment factor works, it's pretty much just a multiplier that is different for every time of the day. And the way we do it is we simply take all the data points for the last 4 hours for that time, and we trying to come up with the best matching multiplier that would bring it down to the prediction range, causing the least number of deviations from the prediction range. And look, that's basically the idea. And we could control it, like we could go 4 hours, 6 hours, so it's all up to the users of the service to do it. That's why having the simulation page on the service was crucial, because you could test all of these things. And in the end, what we do is we alert based on the worst outcome of the two. Either we do it on the adjusted origin, or we do it on the original metric, because it could be that we are below the prediction range or we are above, so anything can happen. Next problem is the known events. As I told you before, we wanted to be able to change our expectations because we know that something is going to happen, right? And we just decided, okay, let's just make it as simple as possible. We didn't want to add any complex logic in the service. We just simply set up some configuration file where we specify some calendar intervals, and the service would then generate additional metric called correction. And the baseline for that metric is 0, so it means no corrections. And then you put some arbitrary value, and service doesn't know what to do with that value. It just simply emits it to Graphite, and it's up to the user of the Grafana dashboard to figure out a way how to use that. And what we did, we just simply treated it as a percentage of how we want to expand the prediction range. So we wanted to give a little bit more in confidence, if you can say that, for the night or for the weekend or for some particular holiday. We could also do it differently, and we could just bring down the prediction range, for instance. It depends on what you want. And the last problem on my list was the complexity of the Graphite queries. So, as I said before, we wanted to make it as simple as possible on the service, give us more room to play with the Grafana dashboard. Unfortunately, it results to this mess. That's actually, well, it's sort of like a real query, but I replaced the metrics with just example metric. And it's only one target on the Grafana dashboard, for the single Grafana dashboard, for the single business metric, where we have like, I think, 10 or more targets, because we want to render different things. Like we want to render the adjustment, we want to render the prediction range, we want to fill the area. So there are a lot of things going on in the Grafana dashboard. And it becomes quickly a mess. And that's not really scalable. So it's really hard to maintain in just this dashboard alone. And it's even more difficult to scale it out to multiple metrics and multiple dashboards. So that's when we realized we need a better approach, and we wanted to try dashboards as code. First, we tried JSONnet, but in the JSONnet, we couldn't find a good solution for helping building Graphite queries, because those were the priority number one, to simplify the building of the Graphite queries in the in the Grafana dashboards. And managing JSON is not that actually difficult, but the Graphite queries are. So what we came up with, we decided, okay, let's just use a JavaScript. In our team, everybody was familiar with the JavaScript, and it's quite expressive language. So we said, and it's very close to JSON. So we thought, okay, let's try JavaScript. that would generate JSON files, and then later on we send them through Terraform to Grafana dashboard. And that's what we did. Like, this is just one snippet of the code. Unfortunately, I don't have time to show all of the Grafana dashboards as code, because we also did the same thing for overrides builder, for the panel builder, etc., for the Grafana dashboards. But this is the query builder, and we just mimic the functions one-to-one to Graphite. So Graphite has group by nodes. So we just put it like this. Sum, moving average, transform null, remove above value, lots of functions. So we just put them in the query builder, and the query builder just works as like chaining of the functions, which if you use Graphite query builder in Grafana, it actually looks like this. So you also have a chain of functions in Grafana, and it's nice that the code was matching that. It was also very easy to well, not debug it, but to analyze what is going on, what is going wrong, and play with the dashboard in the code. So that was very, very useful for us. And with this, once we tackled this problem of managing Grafana dashboards as code, we were able to scale the anomaly detection to multiple metrics. And this is like one of the most important points I want to make is that detecting anomaly isn't that difficult. You can build your own algorithm, you can try various existing approaches, you can try our solution for detecting anomaly. It's not that difficult. But understanding the anomaly might be challenging. And this is why it's important to be able to scale easily and quickly your anomaly detection to multiple metrics, especially if you're looking at the business metrics like page views, orders, anything like logins, etc., user behavior. It's best if you can break it down by as many categories as possible. So for instance, by regions, by country, by device, iPhone, Android, mobile, just in general, user types or marketing channels, any third parties that you use, and then put them on the panel. Maybe you don't put alert on all of them, but you maybe put alert on one particular, like the generic one, but the dashboard will help you to quickly spot the problems. Like in this case, you're already seeing like it's exactly the same metric, but broken down by categories. And it behaves differently depending on the channel. So that's gonna help you a lot. So, because we had examples where, for instance, metric would work fine, but, well, no, not fine. We detect the anomaly on the generic metric, but once we look into the breakdowns, we see it's only the iPhone users or Android users that are experiencing this. So, and it went undetected because none of the alerts triggered. It could be that maybe users just blocked of clicking something. And that's why you want to have this as a last resort to catch the problem, because it might go silently if you don't have you don't have testing in place or anything else. And I'm getting to the end of the presentation. We'll quickly recap. Hopefully, I managed to show you that you can achieve good results with very basic statistical tooling available. So what I have shown you is very basic stuff. There's nothing serious. And you can detect anomalies using this approach. The other one is that this approach works best for the pattern-based metrics, so for the user-driven metric. Because you want to match the same day of the week, right? You also want to match the time of the week. So this is where it works best. Another funny learning is that there are different types of deviation that can give you different results. So I encourage you to look into this as well. See maybe you can find something interesting in there. And we also figured that the Grafana can be used for really complex stuff, but it quickly turns out difficult to manage it. So that's why you have to come up with the Grafana dashboards as code. And last but not least, as I said on the last slide, understanding anomaly is way harder than detecting it. And with this, I'm getting to the end. Thank you.